The API, or Application Programming Interface, is the beating heart of SDVoE, forming the bridge between the client-user interface and the endpoints on an SDVoE system. Now, in the unlikely event that you experience problems when trying to send commands to endpoints from the client software, it's important that you understand why these problems might be happening. This course explains the communication between the client software used to control an SDVoE system, the SDVoE API, and the endpoints, and investigates how to troubleshoot possible communication failures which might occur. Let's take a quick recap of what happens when a command is sent from the client-user interface. In this example, we're using a touch screen controller which contains software which uses SDVoE API commands to tell the API to start an AV stream from a source device connected to transmitter A and send it to a display connected to receiver B. The command is sent to the SDVoE server, which we commonly refer to as the SDVoE controller, and once received, the API server will then send a response back notifying the client that the command has been received. Now, when the API server receives the command from the client interface, it then executes that command by communicating to the endpoints. For example, the user wants to start streaming a 4K 60Hz image from source A to display A. Once the API server receives and acknowledges the command, it will instruct the transmitter connected to source A to begin the stream, and instruct the receiver attached to display A to connect to that stream. However, what would we do if we can't access the endpoints from the client interface, or worse still, the image sent to the display is all distorted? Let's start with the basics. Are all the endpoints and the computer which drives the API software powered up and connected to the network switch? Now, that might seem like a silly question, but if any one of these components are without power, well, they just won't work very well. A good tip when checking network connectivity on any device is to look for flashing LEDs. This indicates data is moving across the network. All the LEDs flashing slowly at the same time or staying on constantly indicates a network problem. And yep, you guessed it, you need to turn it all off and turn it all on again. Blinky lights are good in the networking world. Sometimes network devices appear to be connected to the network, but you don't seem to be able to access them. Now, there are a bunch of reasons why this can happen, like the device being on a different subnet, for example. You can learn all about networks, subnets and IP by heading over to our networking courses on the SDVoE Academy. Using widely available and very simple scanning software will help you determine which devices are on the network, and sending ping commands allow you to check the communication of those devices. This is basic network troubleshooting, and you really should be familiar with it. If you have a background in software development, you'll be familiar with tools such as Postman, which allows you to send independent REST API commands directly to the API server. This example shows the syntax used to query the version number of the API server, and if a response is sent back, we know there is good communication in and out of the API software. Tools such as Wireshark can also be used to monitor the throughput of data packets between the client software, the API server, and the endpoint devices. When an endpoint device is connected and comes online, it sends a tiny packet of data called a hello packet to the API server every 2 seconds. Using Wireshark, we would see this as a broadcast UDP packet from the endpoint device on port 6969. Now, if the endpoint device drops away from the client software and there is no sign of the hello packet in Wireshark, then the device is no longer communicating with the API server. This problem maybe down to a wider network issue, and you can learn more about network troubleshooting on the SDVoE Academy. Making sure everything is connected and the network is correctly configured is really important. As we learned in the Design Partner Certification course, we should carry out some basic housekeeping on the switch to prevent multicast flooding by enabling IGMP v2 and fast leave, as well as disabling unregistered multicast packets. It's also worth checking the multicast table within the switch to see if multiple streams are hitting a single port when only one stream is expected, because this is a classic sign of oversubscription. If the API server is on a different subnet to the endpoints or vice versa, they won't communicate. Now, the quickest resolution is to make sure all endpoints and the API are on the same subnet. It is possible to build an SDVoE system whereby the endpoints and the API server are on different subnets. However, this more advanced use case will require the services of network professionals to achieve it. The term oversubscription refers to when the bandwidth of the streams exceeds the bandwidth available. There are different root causes of oversubscription, and we're going to take a look at some of the most common causes. The control software that you're using should prevent this and show you an error instead, but troubleshooting is about figuring out what isn't working as it should. So let's look at how oversubscription could occur from an encoder or a transmitter device. Certified design partners will know that transmitters are able to send two separate streams to the network: a native stream, which maintains the original format, as well as a scaled stream for features such as multi-view. If a transmitter was already sending a full 4K 44460 stream, which requires 9 gigabits, and a scaled multi-view stream was then requested, this could result in the transmitter sending more than 10 gigabits to the switch, and each receiver connected to either of these streams would see a highly distorted image, or worse still, nothing at all. If this did happen, it's highly likely the transmitter device would disappear from the client software too. When the link is overflowing with packets, some of them are going to get lost, including some of the hello packets. You're probably not going to lose all of the hello packets, you'll just be losing some of them, which will result in the transmitter intermittently disappearing from the client software. Now let's look at how oversubscription could occur from a decoder or receiver device. In this example, receiver C is sending a multi-view image to the display by connecting to 3 separate streams from transmitters A, B and C. As we learned in the Multi-View Explain course, it's important to ensure that the total bandwidth of these streams will not exceed the total bandwidth available to prevent oversubscription. And you can learn more about multi-view in the SDVoE Academy. Remember, network connections are duplex. That means they work in both directions, transmit and receive. As we mentioned before, in the case of the transmitter, which is sending packets of data, it's entirely possible for it to lose some hello packets, resulting in the device intermittently dropping in and out of the client software. However, you could also oversubscribe a receiver and yet still see a healthy endpoint on your software. And that's because the hello packets are moving in a completely different direction to the video packet. The last important point for any Pro AV professional to take away when troubleshooting any IP-based AV technology is to work closely with the IT professionals, because this convergence of AV and IT is key to the success of SDVoE in the future.